Hi, my name is Melissa Ivie, and my project is applying a logarithmic progression to the Fourier transform in order to obtain a logarithmic spectrum analysis. So, as a brief overview of my project, we have the current methods of converging a signal from the time domain to the frequency domain involve this equation called the Fourier transform. Computer scientists and many other scientists, in fact, have taken advantage of this, and it's used in everything from seismic waves and earthquakes to much more popularly audio frequencies, which is what I will be discussing specifically in my project. They've applied it in a different method called the fast Fourier transform, and the result is a set of vectors with a magnitude and phase that has a linear distribution. This is not always the most effective, and my project will primarily be looking into a logarithmic scale instead, because it might be more efficient and practical within the applications of the Fourier transform. The general transform of a function in the time domain to the frequency domain can be expressed by the equation that you're going to see here, and that's just the Fourier transform. It can be applied to a discrete set of values and expressed in the next formula that you'll see there. So, conjecture for this project. The Fourier transform is a way to decompose a signal to its consonant frequencies, and versions of it are used to generate and filter cell phone and Wi-Fi transmissions, to compress audio, image, and video files so that they take up less bandwidth, and to solve differential equations, among other things. It's so often used in digital signal processing, and the math behind it is complex enough that there are very few optimizations that have been done to it beyond the fast Fourier transform. There are times when the spectrum of a signal would be more optimal if it were represented logarithmically instead of linearly. The conjecture of this project that greater optimization of the DFT could be obtained by applying the Fourier transform to a set of samples in the time domain that are spaced logarithmically instead of this traditional linear spacing. For a piano tuner to be able to get within 5% of the lowest frequencies, they would need to be able to tune to 1/10 of 1.635 hertz. So they would need to be able to see frequencies up to 0.1635 hertz apart. The number of samples needed for this would be 20 kilohertz to 20 hertz over 1.635, which means 122,000 samples. Using standard DTF, this problem would be n to the second, or 14,933,328 computations. Using the fast Fourier transform shortcuts, this would be n log a magnitude problem. In order to use the fast Fourier transform, the number of samples would need to be divisible by 2. So the gist of all these numbers that I've been throwing at you is just bare minimum number of computations. So it would need to be 38 sections multiplied by the 32 measurements per second, so 38 times n to the second, or 38 times 32 times 32, which comes out being 38,912 computations. If the same fast Fourier transform techniques were then applied to each of the sections, it would mean 38 times n log n computations would be 1,830 computations. This is a significant improvement over the 670,762 computations that we would be required to do a single fast Fourier transform of the entire series. Well, the DTF formula has a weakness with something called windowing. Here is shown the DFT calculated spectrum for a single frequency. The fact that there's a set of frequencies instead of a single one is because of the windowing effect. Because this windowing effect occurs at the edges of each sequence, performing 38 different fast Fourier transforms would increase this noise level significantly, so there is a setback. This noise could be reduced by increasing the size of each of the segments so that there are fewer of them, or by applying windowing techniques to each of the segments. So, the frequency for a note can be calculated by this F formula, this F of n equals 2 n to the n minus 49. So starting at the 20 hertz and moving in sections of 32 steps, the start and stop frequencies were calculated for each of the 38 sections that would take to cover the entire 20 hertz to 20 kilohertz spectrum. For each segment, a distance between each of the frequencies was calculated at 1/10 the difference between the first and second reference note. These notes were chosen to be the closest fundamental music note that was within the frequency range. The sample period needed to get a full wave of the lowest frequency was calculated along with the start frequency. The Nyquist rate was calculated based on 2 times the highest frequency than the actual sample rate based on getting 32 samples within the time for the segment. The sample rate was well beyond the Nyquist rate, so it qualified that. This could be applied to problems in spectrum analysis, filtering and DSP, so that's digital signal processing, data compression, and partial differential equations. Further work could be done to optimize the fast Fourier transform algorithm, although it could also be applied to a single sequence, but nonlinear progression of the values in time so that these segments could overlap. So the next step in this project would be applying all of this math in the Fourier transform that it's transformed it to be much more effective computationally. I would like to create an app that uses this more applicable method that can be put on your phone so that you can play and write music just from an app on your phone.